scratch says, I mean that scratch record is full.
There's also a group quota, but there's a command called disk usage. Just type disk usage, and it'll tell you the limits and where you're currently at. So just get them to type that and look for. There's, I think it stars even if it's over a certain limit, but it'll tell you the what you're currently at and what the limit is. It's like just a simple quota system.
That's what I thought it was.
Yeah, it just there are multiple quotas for, as you said, files and other stuff. But oh yeah, here I've got this open right now. So the disk, you'll see mine here. So you'll see a whole bunch of listings. But if you go to the first to the top, right at the top here, so you see home, scratch, scratch 2. Now I'm part of the group SIGNET. So you see, and then there's if it's a bar, there's no limit. But so our scratch is 80 terabytes and we've used 21. The number of files is 10 million and we've used 1.7 million. That's for the whole group. And then my individual ones are down here. So you can see my home is 800 gigs and I've used 200 and some whatever. And then my scratch, I've used 1.6 of 20 terabyte. And then here's my number of files, right? So all mine are under that limit, so I'm fine.
Oh, yeah.
Could be. What are you in? File number. It's almost probably files. Yeah.
Yes. Almost.
Is it? There's a 5. I don't know how project is. It's on the same physical disk, but I think it has a different quota. It's a different file set. Oh, no.
Classroom support.
Sorry, we just pressed the wrong button. Well, there's a purging. So the way it works is there's a purging done every month, right? of any data that's over 3 months. But all we do is we run it, and then 2 weeks before we're going to delete anything, we send an email to everybody who's going to get something deleted. And they can either clean up or whatever, make a move or whatever. But it's up to the individual group.
So what they suggest is
The thing is, right now, nobody in your group can do anything.
yeah.
So, right, I mean, even the person who did it is burned, right? So nobody in your group can actually write to scratch right now. So, but with that much, I don't know. I mean, you just have to sort of, but, I mean, it's disk space. There's always an issue, right? So. I don't know how it's. If you're not sure, just send an email to support and Jamie will answer. Yeah, it doesn't surprise me. The big data sets and stuff.
I think it was 6 gigabytes of.
Well, there's some very large data sets like that. There's a lot of experimental stuff. I mean, Mike Nolta's in our group. I mean, they commonly move large amounts of data. I don't know.
Oh no, I'm not saying. Surprised.
Well, because there's always called a hard and soft quota. Because otherwise, what would happen is you'd end up with disk corruption, whereas it hits the whatever. So what it does is it hits the soft quota, and then usually there's a certain percentage of. So then you can't actively start a new operation, but you can finish a current operation. So you don't end up with files cut in half and stuff.
Oh,
It's just a protection. There's always a soft. Sometimes you can set the soft and hard. The other thing too is on our system, we don't, like on your local system, you could set it so that it strictly enforce it for every few megs or every few seconds or something. But on a big petabyte file system, that would be brutally expensive. So what we actually only actively run the quota I think it's every hour. So say you were copying files, you could easily blow through your, quota to a limit, right? So I think that's why there's a few gigs one way or the other, right? The percentage. It's a protection. Yeah, well, you can imagine you were copying a pile of data and the quota system ran, and then 15 minutes later, you could easily move 6 gigs in 15 minutes, right?
it's just like some
Yeah.
and how it's affected.
Some of the some sort of tolerance or something. I don't know.
Yeah,
It's a little bit. It does show up as kind of a funny, but a lot of it there's some soft limits to try to not.
That's reassuring.
Well, it's just
Sorry.
yeah, but nobody in your group can do anything, so you guys got to sort it out. I mean, just. No, I know, but as I'm saying, they can't do anything with what they have right now only, right, either. So it's sitting there as park data, right? So. I think project is, yeah, I think it's part of Scratch.
No, it's not. But do
If you're not sure, as I said, just email support and Jamie, the guy who does all the disk space stuff. He'll figure out who's got where and what access you guys have, and send emails to the right people to say clean up your stuff. Because just email support. Yeah, always email support. I mean, Jamie will be the guy who answers, but just send it to support, because the thing is, Mike Nolta, who works with you guys, works there too, so he might know what you're moving, or there might be some. They may have talked to him too about sometimes when people move large data sets, he relaxes quotas and does. So just, when in doubt, email support. It's not a big deal. It's one of those things. It's just a maintenance thing. It's not. Nobody's going to get mad at you. It's just. This way you can do it anonymously too. So he'll do it, and then he'll send an email to the other user, and you won't get it from you. But he has a way of figuring out who's got all the space in all the group, and I could do it too, but he does this all the time. He would know all those things. So give him something to do. Give him something to do. Keep him out of trouble. Whatever. He does it. That's fine. It needs to be done. I'm not gonna. I did hire a new system in too. I don't know when it's supposed to start. Is it April? Is that what it was? Yeah. Yeah, as I said, they hired. I knew Ramsey saying they hired somebody, and they were interviewing a while ago. I just wasn't sure when it was supposed to start. So. I imagine starting off just doing a lot of the admin crap that Jason can't get around to do. Should be. Well, there's a lot of stupid shit that's just. Yeah, well, that's all right. He's watching right now. No, it's not his fault. It's just there's since Neil left, like there's been short sysadmins, right? What's that? Did he? Oh, I didn't know that. No, recently, oh, that's too bad. Yeah, no, well, he's been gone for 2. You never met him? Yeah, no, because he was here, and then he went on long-term leave. He got sick. I mean, obviously it was something serious, and beyond that, it was just, yeah, that's too bad. No, I didn't hear, but he had a young kid too. He just had a boy. When he first started, he just had a kid, about the same age as my kid, so it's like, kid would be like 4 or 5. Yeah. Okay, well, we should probably get started, I guess. Okay, guys, we're going to get started here. Okay, so today we're going to be continuing our parallel programming section of the course, and today's talk is on MPI. The next 2 lectures are going to be on MPI. You guys the last 2 lectures you went through OpenMP, which if you think back from the original lecture, there was the different types of parallel programming, and so OpenMP is very focused on sort of loop-based parallelism or fine-grained parallelism. MPI, you'll see, is a little more is specifically designed for distributed memory clusters. So this is where you have 2 different systems. You can run it on the same system as well, and we'll do a lot of the tests that way. But what this allows you to do is run it to scale out to the very, very large number of systems. So OpenMP is great. What its major limitation for is you can only do it within the number of cores in a physical node. So that's 8, 16, 24 cores, or how much memory you have. MPI doesn't have that limitation. You can run this out to N, and people have, like in the millions type system. So MPIs, when you want to scale up or go to a large system, you usually end up with OpenMP or with MPI. So we're going to talk a little bit about the MPI. It's a library, so it's a little bit different again too. OpenMP and the other terminal ones were language constructs that are actually built like syntax right into the language. MPI is actually a library. So you're making calls to a remote library, not an actual syntax change. So that's beneficial in some ways and a little annoying in other ways, and we'll talk about that as we go through. Also, along with MPI, there's some ecosystem you kind of have to learn how to use it. You don't just go /run my code with an MPI code. You have to give it some information. So there's a runtime, and there's a different compiler, which is really just a wrapper around your compiler, and a different runtime executable that you'll run. And I'll show some examples. We'll go through the basics of MPI and the main sort of commands you need to get started in some of the terminology. It's not too complicated, but it is fairly low level. One of the major complaints about MPI is that you're kind of writing your own transport layer. It's a communications layer. So you kind of have to do all the bookkeeping yourself. You have to send messages, receive them, and do all this sort of stuff. It's kind of like low-level handling of memory. If you guys have been working in C and C++, so you're sort of used to some of that terminology, but this is sort of, you kind of have to do the bookkeeping, creating buffers and this type of stuff. So it's good in a way is you are actually in there controlling everything, but it's also bad in a way is you actually have to get in there and control everything. Now, luckily, the library has hidden most of this away. And once you run it one code, you can kind of cut and paste what you need. But you still do have to handle a lot of that sort of low-level details. So MPI has been around. It's a fairly mature standard. It first came out in '94. Before that, a lot of distributed memory parallel systems, PVM and high-performance Fortran, there's a lot of different standards for different languages. MPI kind of standardized this. It came primarily out of a group out of Argonne National Labs and a working group, and has evolved ever since. There's version 1. Most people use sort of the version 2 standard. There is a version 3 with some newer directives, but most of those features you're probably not going to use. They're fairly high advanced. The good thing is there's lots of commands, a couple hundred in MPI, but if you know 10, that's probably good enough for most people. There's at least to get started in that sort of stuff. There's some advanced stuff if you really want to get into. A lot of them are variations of a theme. So there's two major implementations of MPI. MPI is a standard. It's not. It's like written by a standards group, and then they get implemented in different variations. The good thing is both of them are free. The most common one you'll run across is OpenMPI. If you install Linux, you probably have OpenMPI, or you can yum apt-get or whatever you want to get that. That's the sort of replace LAM. Open standards, very good. We have that on Signet as well. The current version, I think, is 1.10. I think we have 1.8 here now. The other one that you'll commonly see is MPICH or MPI-CH, depending on who you're talking to. This is out of Argonne National Labs, and it's sort of a more of the research standard. If you work with any commercial MPI, HP, Platform, Intel, any of those ones, they tend, or in the IBM stuff, they tend to follow the MPICH. Now, they both work fine. You can compile both your codes with either of them because they follow the standard. There's just slight variance in the back end of how they work. Doesn't matter is the point. It's like using GCC versus Intel. They both compile C code, same idea. The problem is they're not interoperable. You can't compile one OpenMPI, take it onto your other laptop, and run it with an MPICH. It won't work. You kind of have to stick with one. And the MPIs also have, under the hood, they're hiding a lot of stuff that you don't want to mess with. So on your laptop, you install them, they run fine, but it's tailored to work on Ethernet and on your local system. On Signet, we like you to use our MPI because when I built it for our network. It's network aware. Now, the good thing is you don't have to know. MPI is above the network layer. It doesn't matter if it's on Ethernet. It doesn't matter if it's using shared memory. It doesn't matter if it's using InfiniBand. You can hide all that away. There are flags to do that. But the implementation, like when you compile it to the local system, that has to be specific. So the good thing is you don't have to change your code. You can just recompile it for different systems. However, that MPI runtime library does have to travel with you. So it's a little bit of a annoyance, but because of the nature of it working on distributed multiple nodes, you want to use the local MPI installation. The good thing is not a code level change, just to recompile. And most of the time, the performance is marginally different between one or the other. Make sense? So MPI is a library, so it stands for Message Passing Interface. So it really is an API for send and receive. That's the idea. The distributed memory paradigm is such that these two nodes don't know anything about each other. So I need to be able to get information from here to here to make my jobs synchronized. And that's what this allows. It's an easier way. If you've ever been a TCP/IP information, there's sockets and all this type of stuff. This is kind of like that, but it's a one layer of, and it's very designed for high performance computing. And it very much is designed as to loading buffers, sending information, and that type of workflow. So that's really where it's come out of. So it's been designed specifically for like the HPC type workload. You can use it for other type of things, but you'll see that a lot of the paradigms kind of fit with that type of language. Now, there's two primary languages it supports, C and Fortran. There used to be a C++ standard. You can still find it. However, they dropped it in 3. It was kind of just an add-on to the C anyway. So we're going to, this one, even though I'm C++ code, I'm going to just use the C constructs. So you can do that fine in C++. But you'll see there's a little more C-style operators as opposed to classes and that sort of stuff. The Fortran one, they're all the same sort of functions. You'll just notice that they're all just call statements, but it's the same sort of thing. The only thing you'll difference in Fortran, if you return error statements, they have to be returned through here, whereas in C you can equal here. But otherwise, the functions are the same arguments, and in the back end they're the same. It's just they work either. Now, that being said, if you want to use MPI, those are the 2 native supported ones. Let's say you're using Python. People have written libraries on top of this, MPI for Pi. There's some in R, there's some in other languages as well. But because this course is C++ based, we're just going to stick with the C constructs. But you learn the same terminology, you can use it in other ones. But officially, these are the two supported versions, or supported. And along with that, there's wrappers around the compiler. So you're gonna, when you want to use them, you're using them with a compiler. So if you're using GCC, what you'll do is you'll use MPCC, which is really just a wrapper. It's a shell that sets a whole bunch of flags and stuff that you don't want to have to think about for the MPI. So usually the easiest thing, you could use GCC with a whole bunch of libraries if you wanted to build this yourself, but I don't recommend it. What you want to do is just, when you're building an MPI code, you just replace GCC with MPCC and it should be fine. And I'll have some examples. Same thing with Fortran. And that's fairly standard across the MPIs. Another reason why you want to use the native install to help you solve this up, set that up. So MPI is designed to communicate, coordinate between tasks, and it's done this by sending messages. So each message involves a function call from each of the programs. So in difference, where in the OpenMP, you're just taking a loop and you're breaking it up and it sort of happens organically, you just set OMP num threads. In this case, you actually have to know a priori how many you're going to have, and then you control it. You care about, am I processor 1 or CPU 1? I care about, what rank I am on that list, because I'm going to have to, ahead of time in my algorithm, split up my work. So, okay, numbers from 1 to 10, you're going to be on CPU 0. Numbers from 11 to 20, you're going to be on CPU 2. So knowing the total number of tasks you have in the job, whether it's 5 or 10, is important, how to divide your workload. And knowing, okay, which information I need. My next nearest neighbor, if I'm on CPU 2, is CPU 3, and I want to send him some information, and I need to know where I am and where I'm going. These are sort of the low-level details that you don't really have to worry about with a shared memory system, because you can just copy it in memory. Here you actually physically have to copy a piece of data and send it. So that's what the message passing allows you to do, is literally just hand off. So the trickiest part of MPI, and most people find this, is not the actual MPI language. It's thinking in parallel mechanisms. Like now I have to physically break up my domain and handle where my data is going, and some of the things that can come in with that. So there's 3 basic parts of MPI, or function calls. Pairwise communication via messages. That's my sends and receives. So I'm literally saying, you get a piece of data, I get a piece of data back, or vice versa, and every construct of that. The other type of operations are collective operations. These are useful, say I want to do a sum. So all of you guys send me a piece of data, and then I sum them up. That's a collective operation. Or I have an input file, and I want to send it to all of you. Or I want to take some data from this and some data from this. Those are collective operations that make you, instead of having to write all these individual send and receives that I want to do with everybody or a subset, MPI has functions that allow that to do. The most common ways are your reduction operations. Your sums, your dot products, that type of thing. You can do it with one command, and it can do it more efficiently than me actually writing all those individual messages. The other one is there's some efficient routines for getting data in and out of memory, because we're having to send this, we're doing a lot of packing of buffers. Now, a lot of this has happened automatically for you, so you're just going to load up an array and copy it in and send it. But that sort of rounds out the sort of function calls, you could say, that are in MPI. So, this talk a little bit about what happens with a message. So messages have a sender and a receiver. So these are paired messages. That's what we mean pairwise communications. MPI 3 allows what's called one-sided messages, like i.e. just send something out and I'll assume the other guy gets it. Basic MPI and anything we're going to talk about in this course, is all paired communications. So every time I send a message, my processor beside me has to have a receiving function. Otherwise, it won't work. It'll just deadlock my code. So every time when you write a MPI send, you're going to have an MPI receive right beside it, because you're going to pair those messages. And this is very key to make sure your flow makes sense. So when you send a message, there's certain pieces of information you have to have. It's going to go from 1 to 3. So I need the count, so that how much I'm sending, and I need MPI of some type. So you have to say, I want to send an array of 10 doubles, okay? So I'm going to have an MPI type. In that case, it'll be a double. As I said, this is the low-level stuff. You have to actually tag it for the information, because it has to go and create memory. So if it's doubles or floats or integers, it's going to create different size memory buffers for that. And then there's a tagging scheme. Now, I'm only sending one message. This tag can be any integer you want. So you can just set it to 0 and ignore it. But if I have multiple messages, I have to know where things are. You're going to want to create a tagging scheme, right? So that you know that you're getting them in the right order, so that, message 1, you might be sending 12 messages from processor 1 to processor 3. Well, you're not guaranteed they're going to come sequentially, right? It's up to the network. So you want to give tags on them. It can be as simple as 1, 2, 3, 4, 5, so that you know that you're loading the right data out at the right spot. For simple cases like these ones we're going to do here, it won't really matter, because we're only sending one message at a time. But you can imagine as you get to more complicated schemes, you're going to need to use that flagging scheme. And so this is the paired we actively see. So as I said, I'm going to get into a lot of syntax stuff here. Don't worry about it too much. Think about the high-level concepts. No, you're not going to remember the MPI syntax. It's ugly. There's long function calls. You're going to write it. You're going to pull up Google or this presentation and cut and paste it. Because they're long and there's lots of pieces to it. And I don't even remember it most of the time. But I'm just trying to make sure you know the main ideas that are fitting in here. Syntax you can look up. You type in MPI send into Google, it'll bring you the MPitch page and show you exactly what to put where. But the key parts, or look at some of the examples. I have a bunch of example code I'll show you here too. Those are usually the easiest way to learn for this type of stuff. But I just want to make sure you understand the big sort of concept stuff. So I won't get too bogged down into types and all this type of stuff, because there is some ugly syntax to it. So as we talked about, messages are a string of length of count. So it could be as simple as 1 integer, 1 float, 1 character. This is where it's sort of C-like. You can't send a class. You're like, oh, here, I'm just going to load it all into a nice big data class and top it. It doesn't know anything about that. You actually have to break this down into primitive types. You can, under MPI, create an MPI type, but you have to explicitly do that. You can't just, you can actually create an MPI type of like a struct of any type you want. So you can do more complicated data structures, but you have to manually create that. So if you have a class and you wanted to deconstruct it as an operator so that it could create a buffer to do that, fine, but you have to manually do that yourself. From pure MPI, it doesn't know about those. It only knows about traditional floats, doubles, that sort of thing. So you have a count. It could be as simple as 1, and then an MPI type. This is our integers, floats, point numbers, etc. And then a tag is just any non-negative number. MPI uses the negative number for error codes sometimes, so you don't want to use negative numbers. So the MPI library, as I mentioned, is just a bunch of functions. There's a lot of them, but good thing is most of them are repetitions. They're just variants on a theme. There are like 40 different types of send operators. We don't need to get into the details right now what the different do, but they fundamentally do the same thing, just different ways. The good thing is you can get started with using maybe 6 to 10. So the main key ones are listed here: init, com size, and they all have this sort of, I'll talk about size, rank, and then send, receive, and finalize. And we'll walk through each of those pieces just as we go through here. But the good thing is don't get too bogged down in syntax. You can make a decent MPI code with 6 or 8 of these, and that'll be perfectly fine. So here's an example just to get started here on a basic Hello World MPI code. So it looks like a standard Hello World that you've seen a million times, except for in purple here, I've added some MPI stuff. So the first thing you'll notice is because it's a library, we have to include an MPI.h. That's all you got to do, this one header file. Now the key part is you've got your OpenMP installed and set up. I'm not going to go through that here. I'm going to take that as read. You should use this stuff on Signet because it's all set up for you. If you want to build and compile your own OpenMPI, you can. but there's more steps you need to do to set up. So we're just going to take it. You've got that built up. You're going to use the MPI compiler. So we start with this code. So we include this MPI.h header file. That'll include all the library stuff you need. Before this code, standard C code until, or C++ code until you hit here. The first MPI you have to have is this init, because this is going to initialize the library. If you have any other MPI codes or anything before this, it will break. So you always have to, so the first thing you write is the init. Same thing on the other end, you finalize. Now these don't have to be right before return 0 right at the beginning of your code. You may have a bunch of serial operations and they'd be in the middle, but it's just, you can't do anything in parallel until you start with these two. So they're kind of the easiest ones to put in, and they actually are simple. There's no arguments to this one, and you just pass in the arguments for this one here. So those are sort of the gimmies. You just first cut and paste those and be done with it. Now, the middle ones are usually right after that, and these are rank and size. These are our knobs, and you're going to use these to basically do all your math of how you're going to calculate messages. So the rank, you have an idea what rank, from the terminology, what some of this might mean? So the rank means what CPU I am. So it starts at 0 up to n. So if I start with 10 processors, I'm going to have rank 0 to 9. So I need to know where in that list I am. I need to who I am. This is the who am I. So that's my rank. The other piece of information is size. How many are there? Right? Because if I want to divide up work, the key part is know which on that rank, where am I, and how many total are there. So if I know I'm processor 6 and there are 10 processors, and then if I divide the work in 10, I can know which piece belongs to me. Okay? I'll get into these. We won't worry about communicators and stuff for now, but we're going to take that as read. This is basically sort of a start output here. So that's all you need for a basic MPI code. That'll work. So we can actually look at this. I think I've got here. Well, I have all these examples, and they're on SciNet, and later on near the end of the slides, I'll actually show you how you can get a copy of these and work on this data. But so this is that hello world code. I think it's MPI. This is just pretty much the same as what I've got there. And then we're going to run it. So when I run an MPI code, I actually have to use MPI run. And then the only flag I need to give it is I have to tell it how many processors do I want, right? So at the very minimum, I could have 1. Hello. Okay, so hello task 0 from 1, right? Because you're always going to have rank 0. Because if you're going to run, you're going to at least, because you can guarantee, you'll see that in a lot of MPI codes. If rank equals 0, output something to the screen, because you're guaranteed to have rank 0. It's the only one you're guaranteed. Everything else you don't know. But I can increase this. Now they all output task 1 of 4, everything else. Okay? So now what's actually going on, and this is something different again, when you were writing your OpenMP, it would actually start with one process and then spawn out multiple tasks. The MPI are completely separate processes. Full-fledged PIDs, you open up top, you're going to see n of those processes on each processor. So they have their own memory, they're launched as full-on processes, and effectively they're a whole pile of serial, they're just coordinated as a bunch of serial tasks. The only thing that's connecting them together is the MPI. That library is handling the point-to-point communication. Now in this test, I'm on the same node, but it really wouldn't matter if I'm on the same node or I'm across multiple nodes. It's handling the bookkeeping for you. But the important part of that is, and when we look at an example here, is until this point, and after this point, they are running completely independently, right? They're serial tasks, they have no synchronization. So when we run them, and actually literally every code goes through the exact same code base. I mean, line by line, just a serial execution. And these actually, because there's no synchronizations, except for here and here, they can happen at different times, right? And so they can output, because they get their rank and size and they output it. And that's why if you look at the output, if I run this multiple times, you'll actually see I get 1, 2, 0, 3. And if I ran this again, I may get a different pattern. Now I get 2310 because I'm not synchronizing anything there. I'm just saying go for it. And that's fine because in this case, there's no data dependencies. But you can see where we're going, that if you care about which happens first, you have to control it. And also they're just going to go to the buffer. So sometimes debugging can be a pain too, because you don't know which one's going to go first unless you're controlling. So these are some of the low-level pains that come with MPI. Yeah. Well, in the sense they are, but the work is independent, right? So they're synchronized in one sense. When I do my MPI init and my MPI finalize, it's sort of intrinsically connected, but the work in the middle here is not, because I can go and ask my rank completely independent of what everybody else is, because that's all determined at the runtime at the beginning. So these are in the stuff in the middle here. Yes, there's no synchronization. These don't have to talk to each other. They're effectively serial processes, right? Yeah. No, you can oversubscribe it crazy. You're just going to step on yourself. So on this machine, here's an example. This is one of the SINET nodes. If we look at it, it shows up as 16 cores, I think, because there's hyperthreading, but they're 8-core nodes. Yeah, so it shows processor 15 because they're. So I can put in 16. I can put in, because what it's going to do, you would normally don't want to do this, but it's just going to oversubscribe it, because once again, we're not synchronizing, so I can go to town on this. Well, depending on your program, and if you looked at this in the background, it's launching 24 tasks, right? So there's only 8 physical cores. Now this is trivial, so it doesn't matter. So if you want to test something, sure, go ahead. But it is better to match usually physical cores, depending on your workload, because especially when we talk about communication. 8 in this case. So that's why we run something at SINET. You'll see from batch scripts and stuff. If you ask for 8 nodes of 8 cores, so NP is usually N times PN, so it's always 64 or 128 or something like that. So working in powers of 2 make life easier and also makes communications easier. Running MPI run-7 10 times can cause problems depending on your grids and domain. So working in power, you almost always see powers of 2. But yeah, there's no reason you theoretically can't oversubscribe it. And it, like for testing like this, fine, it's not going to hurt anything, right? Because they're synchronous, they're not going to block it. Okay, so this is how I built. This is just an example. Don't worry about the details here. This is for you for later. If you want to go in and play with this, you're going to have to go back through this when you want to test these. You can go on to SINET with your account. You can clone out these copies of this example. There's the modules, and then there's the command line of how you compile it. There's a make file there too. It compiles exactly how you'd expect it. Any code you can compile with your GCC command line, libraries, everything else, you can drop in, replace the MPI CC or variant otherwise, because this is just a wrapper. If I type MPI C++-V, it's going to show you the GCC output, because that under the hood, that's what it's doing. It's just going to save you some work. That's just, if you look right there, that's just my friend GCC, right? Gives me the same thing. It's just the MPI. You're going to save a lot of work not having to link in all the libraries, and you can see it if you're really curious. You do a witch of that MPI CC. It's just a shell script that has a whole bunch of junk in it. But save yourself the trouble and just use the tools the way they're meant to. And that's pretty standard across most MPI, just because it is messy. There's a lot of libraries that have to be linked in that you don't have. Okay. So, okay, so that's the main pieces of building. Works very similar. So there's nothing too fancy about this. It's just a library after a little bit of process. MPI run. MPI run in the launching system is actually quite a complicated system, because this has to be able to do a bunch of things. It has to be able to talk to multiple nodes. So it's got to be off-node communication. It has to handle in shared memory. And it also has to do the bookkeeping between all your tasks and all this type of stuff. So there's actually quite a bit that MPI run command does. And effectively, it's just a job launcher, right? And so what it's doing. So the very minimum you need to give it is, well, actually, you could, if you don't give it anything, I think it'll assume 1, depending on the variation. It's a number of processors. There's a lot of flags you can give MPI run, because you can imagine you can control communication stuff. If you're going to be running hybrid code, you can tumble number of tasks, number per node, all this type of stuff. And for a multi-node list, it has to know which nodes you're going to use. So on the same node, it's fine. But if see, in that last case, I only gave it one node, so it launched all 24 on the same node. What happens if I had 3 nodes with H cores? How do I do it? Well, the good thing is the scheduler, when you submit it in the scheduler, it fills in all those node lists properly. There's actually something called a machine file in backend where actually it gives all the names of the machines you want to be part of. So it actually has to go in and do all the initially start up, log into each of those nodes by hand, set up a little daemon on each, and then launch the pieces. So it's doing a bunch of bookkeeping. Now, so that's what we did here. We've already gone through this. It's almost always equal to the number of processors, but it doesn't have to be. So we ran this as an example, and it works fine. So I'm just going to put 4 here. Now, the interesting thing about MPI is I actually don't need if I do an ls here, right? I can actually do MPI run dash np2 ls. That works too. I don't even need an MPI code right here, where it's just, you see it just runs the command twice. So that can be useful using MPI, even if you don't have MPI commands. It might be useful for batch processing for you too. You may have a bunch of stuff you want to launch out with a parameter file, and the tool is already built for you. So it already has this ecosystem there to be able to launch jobs. Sorry. So number of processors. So yeah, I don't want to get into too much of the details of MPI run, because it's its own other but actually, there's quite a lot of flags for millions of things that you don't want to worry about. But for the very basic stuff, so -n or NP is the number of processors to run. And then, so that's the one. You can control a lot more details than that, but usually that's the one you care about, and the rest of it, the defaults are fine for most people. Okay, so when I run ls, when I do a command like ls normally, right? I get one output because I launched one program. But when I told MPI run to do it, how many did I ask for? So what did it do? It ran 2 copies of it. Because it's just a serial code, you just get n copies of it, right? So if you wanted to run 10 of the same thing, you can do that. So even though, because the MPI run and the MPI in your code, separate things. Because the MPI init in your code is actually what hooks up to connect all your threads together. But you could actually use MPI run to launch, it's setting up the ecosystem environment variables and stuff, but you can run any code. It doesn't have to have MPI code in. It's just sort of it's a bigger construct, is what I'm saying. It's more of a flexible. Most of the time you are, but it is sort of a separate piece is what I meant. Okay, so as I said, this is just an example. You can run hostname, ls, whatever you want to run different jobs. This is just showing you the MPI run is a separate executable that is really just like an SSH, but is set up to do a whole bunch of stuff for MPI jobs. So this is sort of that other stuff on top, not really related to MPI, but it's just they're the ecosystem to be able to use it properly. So we've already seen this. There's a niche command here too, because you can tag the output. This is in the OpenMPI, where you can add this flag, and this is useful for debugging because it actually tells you the message tracking where it came from. So this is kind of useful for knowing, because you can see here, this is it actually, in this case, we're outputting the rank, but you could actually just have a code that says I'm calculating something, and I don't want to have to write in printf rank size all the time, right? If you use tag output, it gives you that by default. So if you're debugging, sometimes that can be useful. So that's just a nice command that can be useful, where you don't have to actually go in and write rank output in all your output in your debugging sort of information, if you're doing it by hand. Okay, so this is back to our hello world. We've got our init, we've got our finalize, we've got our rank and our size. But right now, we're not doing any communication, right? All we're doing is setting up a framework for us to send messages, but we're not actually doing any message passing. These are just independent tasks. So We've included the init, finalize, we've got our error codes here, and then we've got these communicators. The communicator is just a group of processors that want to talk to each other. Okay, and the default one is COM world. By default, when you start up an MPI job with n tasks, they're all part of the same communicator called COM world. So for most of what you're going to use, the only communicator you're ever going to care about is COM world. Everybody can talk to everybody. But there may be cases in the future where you're like, okay, we're going to break off into groups, and you guys are going to be communicator left, and you're going to be communicator right. And then we can make messages that only work within this group and only work within this group, right? Now that's useful for, if I'm having a really big code, I may not want to send the same piece of information to everybody on the whole, party telephone line here. I may just want to do it for my subsection. But for a lot of communication, COM world is perfectly fine. And you'll always have COM world. You don't have to create it. It's not a separate communicator. But MPI does allow you to, it has a system to allow you to build your own communicators. So that's why, so for most of these cases, you're going to see all I do everything with is COM world. So that's just, everybody can talk. I can access everybody. I've got a list of every processor that I'm actually part of this group. So yeah, it groups that processes into communicators. Each communicator has a number of tasks. So in this case, it's 4, rank 0 to 3. Each task, has a rank, and then we just said they all part of COM world. So these guys are all part of COM world. I could create a new communicator because I don't like processor 3. He's always doing something funny, so I want to, that's Marcelo over in the corner. So we cut him out of our communication, and we only want to make a new communicator, and I can do that. And you can imagine a lot of algorithms, there's reasons to do this, to sub communications out, and it allows you to do that. Then you can work on just your individual sub communicator. You may not need to do this, but the framework is there to do that. So communicator components, we've talked about this, COM world, rank, my current rank, communicator size. Rank and size are much more important, as I think I've been kind of beating the dead horse here, are way more important in this than OpenMP. OpenMP, I don't care what thread I'm. I just say there's n threads and do my do loop, and I do my parallel loop, and it breaks out. I don't really care which piece does which. In this one I do, because I have to manually send, you get this data, you get that data. I have to actually do that partitioning myself because of the distributed memory nature of it. So a lot of your bookkeeping and a lot of thinking about MPI is thinking about how do I break up the data and who goes where. Syntax itself is pretty easy. Once I know who to go where, it's pretty easy to write one function call to send, okay, here's a piece of data, send it left, send it right, whatever else. So how do we do that? So the thing we're going to introduce is the fundamental sort of MPI tool or function that actually does some real work. That's the send and receive. And now, as I talked about, we're talking about pairwise communication. So I never just talk about send or just receive. I'm going to talk about both of them at the same time. Because whenever I program one, I need to program the other one. I can't just throw stuff out there. I always have to have somebody to catch it. So this is the top here. This is a prototype of a send. There's different types of sends, synchronous and bulk sends and buffered sends. But for now, just consider one's a send and one's a receive. And they involve a couple of different parts. The first one is a pointer to a message. Now, a message is essentially just a buffer. One-dimensional, or it could be two-dimensional, but primarily one-dimensional buffers of size n. Count is the number of elements in pointer. So I make a float buffer size 10. That's a pointer to the beginning, and that's the number of elements in the pointer, so that would be 10. MPI type, I was going to say it was floats, so whatever it matches, I send it as floats. And then the destination. So this means when I'm sending a message, I'm the sender, so I don't have to tell it I'm come from processor me. It's already there. But I have to tell it where to go. And that can be trickier than what you want. But say if I have two processors, it's easy. I'm 0, you go to 1, or you go to 1 and go back. But you don't know. If I have 3, do I go to 1 or do I go to 0? If I'm 2, you don't know. The tag, as I said, this is just an integer. It could be 1, 0, it doesn't really matter. You can ignore it if you want, but it's useful for other stuff. The communicators we just talked about, most of the time it's going to be COM world for what you guys are working on, but it can be other communicators. And then there's a status. There's a way of checking errors and sources and some other stuff, error code checking stuff. But the key thing here that we've added is now we actually have to have a buffer of information we're going to send, our message, and where it's going. And the receiver is basically the reverse of that. It's just the receive pointer, everything else should be the same. As you can see why you'd want to program the two always at the same time, is because they're basically, you can cut and paste one, and then the only thing you're really going to change is this guy, right? The rest of that information should be exactly the same. Now, that being said, your receive pointer has to be a buffer that's ready to get it, right? It has to be created and it be empty. Otherwise, if you're sending multiple messages, you could be overwriting yourself, right? But in terms of structurally, though, the only thing that's really going to change is the logic of where the source comes from, or the destination. But it does make programming this and thinking about it if you're always literally having them together. There might be some if statements in between these, but the idea being is you want to program them in together. So here's an example of one. So this is the same sort of code that we had before. Include our MPI.h. We're going to add a few more pieces up here to handle more data, but we have our init. We figure out where I am, how many messages I have, and we're going to create some dummy messages. Just simple integers just to create something to send back and forth. So I'm going to send a 111 and I'm going to receive a 999. So I'm going to do something dumb that you normally don't want to program, but we're going to do this. We're going to hard code this in as a job that only really works on 2 processors. So at the very basic, I say if I'm rank equals 0, so I am rank 0, I'm going to send a message. So I'm going to create a send. I have a buffer message sent. It's only one line and it's a double. And I'm going to processor 1, which I've hard coded in here. Okay, straightforward enough. Then so when the code runs, it's going to go in here and send this message and then end. And then on the other processor 1, it's going to ignore this, right? Because I don't satisfy the is condition, and I'm going to run this part of the loop. So I'm rank 1, I'm going to receive some message of size 1 and then output it as well. And then I'm going to finalize. So in general, you don't want to do this for every message, but this is a teaching example where I can break all the rules and do things that normally make sense. Okay, so let's run-mp2 first. Get the first message. Okay, so there we go. Hello, so send from 111 and receive from 111. So if we look back at this code, because my message received originally was initialized at 999, so we've overwritten that. So that's why we end up with 111. So this just illustrates the idea of a send and receive. Yeah, this is not doing a whole lot of practical work, but you get it. It's not very complicated. Yeah, this is ugly. It is. Don't get me wrong, it is. And you're not going to remember the syntax, and you're probably going to make a mistake somewhere. But luckily, most of those will be worked out at compile time. The trick is figuring out this logic here and getting these, destinations correct. This here and here. That's the trick, or usually I find anyway, of using MPI is working out that logic. Okay, so let's go on. So there are a couple key source destinations you can use too. It doesn't have to be 0 or 1. There's also some nice ones. So proc null. You can basically send a message to proc null, which means it just won't go anywhere. They'll still satisfy it, but it won't go anywhere. You're like, why would I want to send a message to no anywhere? Where this comes in handy is, say I've got a for loop from 1 to 1,000, and I just want to send all my messages to the left, 1 to 2, 2 to 3, 2 to 3 to 4. Well, if I had to stop at the end and say, oh, I'm on the very last processor, I don't want to send anything, I'd have to actually put another if statement in my code saying, okay, you're the last one, skip it. What this allows me to do is, I'll just throw in proc null for that last message so that my nice code structure stays exactly the same, but I don't actually have to put in that if statement, right? So it makes procedural programming a little easier. Same thing with any source. It's like a wildcard. It can go to anywhere. So these are just sort of nice features that make loop-based programming a little easier and makes your code a little less ugly. And we don't want to put if statements and branches in our code, so we don't have to. And you'll see where these come in handy when we talk about boundary conditions and stuff. So here's an example. We're going to talk about a lot of left and right sending. So this is sort of a 1D example, and this is very practical in a lot of the type of program we do. We always start out with, say I have some grid-based problem, Very simplest is in 1D. I've got a series of cells. Well, if I'm doing this in multiple processors, I'm going to break this up and do this work across multiple processors, right? So I'm commonly going to send data here and here, right? So if you think about this, in 1D, this is really just sending messages left and right. Simple number line. I have some numbers from 0 to n-1, and I want to divide the work up. So if I have 3 processors and 9 cells, everybody gets 3. But these guys have to communicate at the end because I have some pieces of data of information that I might need to go back and forth. Say some finite differencing or something like that. You can see this. Now this, of course, expands in 3D and 2D and whatever you want, but they're really just multiple variations on the same thing. In this case, this illustrates the point here. Okay, so 0 to 1, 1 to 2. That's where we're going to send all our messages left. So let's rewrite that base code. The first part of the code looks exactly the same. Init, com rank, com size. But now we're going to do a little smarter. We're actually going to make something arbitrary, not just 0 to 1, 1 to 2, and a bunch of if statements. So this is where the logic comes into. Our message passing looks very similar, right? The only thing difference is we're sending a message. It's still of size 1. We still have a received message. The difference is our source and destinations no longer are hard-coded. We're going to work some logic into them so that the same piece of code will work on n processors, right? So what I have to do is, this I said, this is where all the logic and thinking about MPI code usually comes from. So I have a leftmost neighbor. So let's just say, looking at it this way, my left guy is over here. So he's going to be rank -1. And my right is rank +1. So I'm this guy. So this guy, let's just do this as, so I'm processor, so this is P. So then of course this guy is going to be -1, this guy's going to be +1. So in this lexicon, it's basically everything's on the left or it's on the right. Standard grid-based stenciling type idea. Okay? And this is where we're going to use these terminologies of proc null, is to make this so I don't need to put if statements in here. If left is less than 0, we know there's no processor over here, right? We know it's not existing, so we're just going to send that flag to null. And then on the other end, we're going to set it to null as well, because it's greater than the number of processors we have. So that's just to take care of these endpoints, right? And you can imagine when you start doing boundary conditions, this could be useful. But it keeps us, we don't have to write these MPI codes any different. We can just use the same thing. And then we're just going to send a message which is double the rank. And then we're going to initialize the buffer just so that we know if it's still 1 -999, we didn't copy anything to it, right? So is there anything weird there? I know it, don't worry about the logic too much, but you just get the idea. That's where the work is done in that pass to the left function. So running second message here, we run it with 3. We get, 1 is sent to 1 and it got 0 because remember, it's rank squared, right? Let's go here. So it gets 1, it got 0, 2 gets 4, 3 gets 9, be straightforward, right? And it got 4 because it's on this side of 2, right? And then we only sent left. So this guy didn't get anything, right? Because he's way over here, and we were only sending messages this way, right? So he never got a piece of data. He's all by himself. He's like, I'm stuck at the end, and I get no messages. No mail for me, no Valentine's cards. Okay? But you get the idea. Now we can do something that's n-based without too much trouble. Okay, so this complete the loop. Yeah. No, because what you're doing, if we look at the code, cout is after the receive statement. So procedurally, you're outputting message received, right? This is not going to happen until after this happens. This is called a blocking receive. So it can't go forward until it gets its message. We'll talk about blocking versus non-blocking. But in this form of it, it cannot go until it's successful. Now, properly, I should be checking on this I error, right? Because if I got this as a failure, you're right, I could say this message got screwed up and never got sent properly, then I could do that. But outside of this being wrong, this is perfectly fine because it won't, these are serial codes, they won't go beyond that until it fits it. It'll wait, it'll pause until it gets that data. And that becomes an issue, but you can see. Well, what I'm setting up are the tags. So this is just who's I'm sending from the right going to the left. So I'm setting up the sources and destinations. Remember, this is the bookkeeping that I have to do with MPI. I have to always come up with the pattern. So in this case, I'm going from left, or this is, I post the sending from right, going to left, right? So those are all going the opposite way. Okay. So this is just the bookkeeping, sources and destinations, and that's the ugliness of it. The rest of this is pretty, I mean, it's cut and paste. You don't mess with it. It's just, I create a buffer, it's a double, and it's pretty straightforward, just like anything else. The tracking the source and destinations is what's going to make you pull your hair out. So that's that case. So now we want to do a periodic BC because that guy's lonely over here. And normally we want to copy some data out of this one and then complete the loop and put some data back on that side, right? And that should be pretty straightforward. Right? All we do is, let's change that working size. So instead of up here, if you looked at here, we were just sending it to proc null on both ends. If we wanted to wrap it around, well, that should be easy enough, right? All I do is I'm going to go change this. So now I'm going to send, if I'm less than 0, well, I'm just going to set it to size -1. So if I'm over here, I'm going to fake it out, just like any other periodic boundary condition, and send it this piece of data, and then vice versa. So that you're like, yeah, that's perfectly fine. I do that all the time, no problem. And you're right. But let's I think I just buried the lead there, but let's try that. MP2, third message. Uh-oh. Is it because Synapse really slow, or what's going on here? By 4. No. So, welcome to MPI. Press enter and nothing happens. Well, what we've done, just like writing a while one loop, you've created, instead of an infinite loop, you've created a deadlock. And you're like, what do you mean by that? This is the most classic and commonly one you're going to run into. This is called a deadlock. And this happens when a cycle of tasks are waiting for other routines to finish. And so anytime you see a closed loop, like this diagram here, you have to break it somewhere. Remember, we're doing paired messages, sends and receives. They have to match, right? So we have to have some way of getting one to complete before the next one can continue. Because as you just pointed out, I can't go to that receive until that send is sent. So when I'm only doing it one way, that's fine. Because the way it's going to work is it's going to go send, 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 and the receives are going to go back, 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 and life's good. Maybe not the most efficient thing in the world, but it can complete. The problem here is this guy he can't start his receive until this guy's sent, and I've got to physically break that somehow. Okay, so this is a diagram of what's going on. So you remember, these are all running independent tasks. So processor 0 says, fine, I'm going to send a message, you're going to send a message. Okay, you send, and you're waiting at the receive because I've got it, right? But then what happens is now I fill back. Now I've got the receive, we can go back, I can receive, now I can receive, and we're all good. This is the one that works, right? Now we're going to add that extra loop. So they have to be, this is the whole tied to parent send. I think we're going to end here, and I'll pick up the rest of it after talking about buffering and how this works. I had to fix that. I'll leave you hanging. Don't worry. Okay, MPI is screwed. I'm teaching you it's useless. No, there is a way to fix this. You can imagine there's different ways of splitting it up. You can do evens and odds. There are other paired messaging. But just like you had pointed out, the fact that it can complete, that's a feature, but it's also a bug, is that it will cause you a problem. You have to actually break up that ring somehow so that it can complete. Because when you have this case, if you can't have this guy getting to receive, somebody has to get receive first. And if you have a loop, where does the receive start? It doesn't, because it's a loop. It's a closed circle. Anyway, so there are ways to fix that. It's just this is going to come up. Ah, exactly. Yeah, everybody sent something. We're all sending. So if I attached a debugger, where it would show, I mean, you could see this. I don't want to get into the details, but this code here with that pattern, when I attach the debugger, wait, because I can never get to this guy. As soon as one gets here, then it unzippers and we're all good. Right? Anyway, we'll talk about that on. Well, the other thing I just want to mention, we have a parallel debugger called Linea DDT at SciNet. Tomorrow there's a webinar series. You should probably see it on the education site. We'll probably send another email. But it's talking about, they make a couple products, a parallel debugger, which is very good because you can imagine solving these type of problems is a little tricky with a traditional debugger. They have a parallel debugger we have a license for. They also have a program called the Linea Map, which is like a performance tool. So it actually configures out where you're spending time in MPI codes or even in your regular code for performance, like gprof type stuff. So they're doing a webinar tomorrow for about an hour. So if you're interested in that type of stuff, especially as you get to scale, it's a very powerful tool. It's one of the few pieces of commercial software we pay for at SciNet because there's really not a lot of good open source tools for debugging this stuff. Now, regular debugging GDB works fine, but if you have to open up 12 windows and try to figure out what's going on and press enter in every one, it becomes a real pain. So they've developed some pretty good tools for this type of stuff. So if you're interested in that, you can come by SciNet tomorrow afternoon, and we're doing that. They're having one of their guys is doing a webinar on those performance tools and on the debug itself. Okay. There's the, oh yeah. Okay, I'll let you do that.